Thus far, we've referred a lot to the distance that stars are from us. So in this video, we're going to survey the methods for measuring stellar distances, the ways of figuring out how far away the stars are. Well, this is a question that ancient astronomers asked themselves as well. But they didn't have the tools to see something called stellar parallax, which is the shifting in the positions of the stars that occurs from changing the viewpoint. So if you look at a star when Earth is at winter versus when Earth is at summer, the parallax should shift a little bit if the stars are at some distance away relative to the stars that are behind it. But ancient astronomers could see no stellar parallax. What they didn't appreciate was just how far the stars were away, and their limited naked eye observations were not nearly precise enough to see those shifts. But now we have several methods of estimating how far they are away, and in brief, they are really, really far. In fact, the closest star to us beside the sun is 4 light years away. So it takes 4 years for the light from that star, which is Proxima Centauri, to get to us. Now, if we go just within our galaxy, go from one end to the other, that's about 100,000 light years. So the star that's on one end of the galaxy sending light to the star on the opposite end of the galaxy, it takes 100,000 years for the light to go that distance. And that's just staying within our galaxy. If we go outside the galaxy, then we're talking about even more immense distances. So let's start close by, and then we'll move our way to greater and greater distances. If something is in the solar system, what we can do is bounce radar off of the object and let it reflect back. So this is sort of the most direct way to measure the distance to something. You send out a radar signal, it reflects off the object, you know the speed at which the radar radio wave is traveling, the speed of light, and using the time it takes for the signal to get back, you can estimate how far away the object is. So in this example here, if it takes an hour for a radio wave to reflect off Jupiter and return to Earth, we could estimate 540 million kilometers away. Now, how do you get there math-wise? This is the radar ranging calculation. The distance to the object would be the speed of light times the travel time. So speed times time gives you distance, but the distance it's traveling is actually out and back, so you divide it by 2 because it's a round trip. The speed of light is this number, 3 times 10 to the 5th kilometers per second, 3,600 seconds in 1 hour, divide by 2, and you get 5.4 million, so 10 to the 8th would be 100 million kilometers away. All right, so radar ranging is a direct way of determining the distance to something. You just have to send a signal, let it bounce back, and use the time it takes for the signal to return to calculate what the distance is. But that only works if you can bounce something off of it. For stars, you can't reflect light off of them. And they're too far away really to make that worthwhile anyway. You'd have to wait years for the signal to come back to you. So we need better methods. So I mentioned parallax. This gets into that parallax in a little more detail here. So let's take a look at the picture in the upper right first, because parallax is something we can use terrestrially on the Earth to measure the distance to things. And so surveyors will use parallax to measure the distances on properties, for instance. So we have two vantage points here, and we're looking from those vantage points to the same object, this tree right here. The distance between the two vantage points is the base, what we call the baseline. And then from these two, you can measure this baseline directly, right? So presumably in this setup, you would know the baseline. You would have that number. What you'd want to know is how far away the tree is. Okay, so what you can use to estimate that is the fact that this angle and the baseline are essentially two quantities that are representing this big triangle. And if you know a little bit about trigonometry, knowing those two properties is enough information to figure out everything else about the triangle. And so this process is called triangulation, and from it you can determine this side of the triangle, or the line down the middle, or this side of the triangle, whichever one you want. You can figure out everything about the triangle by knowing two properties, the baseline and measuring the angle here. Okay, so now let's go from this picture to the stars. We can create a similar setup with the Earth's orbit. So if you're over here at point A, looking at a star, and over here at point B, looking at a star, its position in the sky relative to the stars behind it is going to move. So as seen from point B, this red star, project the line back into space, is sort of just to the right of this star, right? Or I guess just below this star. But from point A, if you project their line of sight out, its position has changed. It's not over here anymore, it's up here. And so it will shift back and forth. This is the parallax shift. So we know the baseline because the baseline is essentially the diameter of Earth's orbit. And if we can measure precisely the angles to the sun, to the star in the sky, then we'll have this angle, and that allows us to estimate the distance. Now specifically the parallax angle, what we call the parallax angle, is not this one, but it's the skinny angle here. So this is called the parallax angle. Okay, so what does the calculation look like? We have 2 points. So here are 2 points and a baseline. Let's call the baseline B. The distance to the star is D. And the parallax angle is the skinny angle in between the two. As long as this angle is measured in radians, the distance to the star is essentially that baseline divided by the parallax angle. So pretty simple calculation. The Earth's baseline is 2 AU, right? Because the Earth's orbit is 1 AU from the sun, and so it's 2 AU fully across. Alpha Centauri has a parallax angle of 3.665 times 10 to the minus 6 radians. It's just an incredibly small parallax angle. This is why ancient astronomers weren't able to detect it. But if we plug these numbers into that calculation, baseline of 2 AU, parallax angle of this, we can calculate that Alpha Centauri is 545,703 astronomical units away from us. All right, so that's the basic idea of stellar parallax and using triangulation to measure the distance to stars. Okay, now these angles are going to be very, very small, which means the distances are going to be very, very large. Measuring the distances in astronomical units or even kilometers, that doesn't make a whole lot of sense. Astronomical units are useful within the solar system, but outside of the solar system, the numbers get so big, we need to go to something different. Now, what we've used so far is light years, but there is another unit of distance that's pretty common in astronomy, and it's called the parsec. It's based on this idea of stellar parallax. The distance of a parsec is the distance for a star that has a parallax angle of 1 arc second. So let me say that again. If a star has a parallax angle of 1 arcsecond, its distance is exactly 1 parsec away. Okay, so what is an arcsecond? An arcsecond is 1/3600th of a degree. Right, and so that's the idea of a parsec. It's similar to the light year, but it's actually even bigger than a light year. 1 parsec is about 3.26 light years. So it's a very large, so as far as we've encountered so far, it's the biggest unit of distance that we have. So a parsec is the biggest distance of unit that we have. And so it's appropriate for measuring the distance to stars. But I tend to prefer light years, so I use that a little bit more commonly. In astronomy generally, both units are used, light years or parsecs, or either one is appropriate for measuring the distance to the stars. But the parsec is a little bit more natural for using parallax to measure the distance to the stars, because it's a simple calculation. You measure the parallax angle, that immediately gives you the distance in parsecs. Okay, so far we have the radar ranging and the parallax as ways of measuring distance, but they run out. Eventually, you can't use radar because things are too far, or they don't reflect the radar that you'll send out, or you convert over to parallax measurements, and those things get so far that even our best telescopes can't detect the parallax angle, and that can happen as well. Eventually, things get so far away that we can't, even with the great technology that we have today, we can't measure the parallax angle. There is a limit to how precisely we can still measure the stars. But luckily, there are more methods of determining distance. And the next one we have is using a type of star known as a variable star. Now, it's called a variable star because its brightness varies over time. Now, connecting back to what we said about HR diagrams, these would not be stars on the main sequence, because stars on the main sequence have very, very specific relationships between all their properties. They're burning hydrogen, they have a certain mass, a certain radius, a certain luminosity, a certain temperature. All of those characteristics are really well understood, and how they're related to one another are really understood. But stars off of the main sequence can behave in different ways, and one of the more important ones is variable stars. So we didn't do this HR diagrams activity, so you can just ignore this statement right there. But we will use the ideas of variable stars, and they were first their first utility came about in 1908 with Henrietta Leavitt, who discovered that there was a relationship between their period and their luminosity. So the period being the time it takes to go from brightest to dimmest, back to brightest to dimmest. That cycle, that time, so from here to here, this time, so the period of this variable star that's being plotted would be from about 3 days to 9 days, so it would be a 6-day period. Well, that period is directly related to how much luminosity it has. And the types that have this specific period are known as Cepheid variables, and that luminosity allows us to know the distance to the star. Now, you might not see that directly, but think about what luminosity means and what apparent magnitude means. Luminosity is how bright a star really is. Apparent magnitude is how bright it appears to be. So we always know how bright a star appears to be. We can always measure the apparent magnitude. If we then know its luminosity, the third variable there is distance. So we would know 2 out of the 3 variables. So if you have a star with a very low apparent magnitude, meaning it appears very bright, and it has a low luminosity, meaning it's not producing a lot of light, then that star must be really close to us. And there is a specific equation. We're not going to use the equation, but there is a specific equation. Once you know luminosity, you can calculate the distance to the star. So this type of relationship is called a standard candle, or this type of star that has this property where its luminosity is known is called a standard candle. It's candle like a candle that you would light in your home. And it's standard because we know exactly what the true luminosity is. Standard candles are a powerful tool. Anytime you have a standard candle, something with a known luminosity, you can calculate its distance. And that means all you need to do is see the star. You don't need to measure like tiny shifts in its position, its parallax angle. You don't need to bounce anything off of it. All you need to do is be able to see the star. If you can measure its luminosity, you can measure its distance. Okay, there are other types of variable stars that have similar relationships. Another type is called the RR Lyrae. They can be used as standard candles, but they're not quite as good standard candles as the Cepheids. So if you look at the plot here, you can see that Cepheids have a range in periods and a fairly tight relationship between what the period is and what the luminosity is. For our Lyrae stars, they have all about the same luminosity. And so but there's a little bit more scattering in the data, so they're not quite as uniform. But in either case, they give us ways to estimate luminosity and then from there calculate distance. The process is sort of illustrated here in the cartoon. You can see the astronomer looking through the telescope, figuring out, what the period is. So I think she has a stopwatch in her hand here. So she's timing the period. Then she comes to the chart that tells her the luminosity. She plugs the luminosity into the computer, looks up the apparent magnitude, or maybe she finds the apparent magnitude here as well, and then plugs it into calculation to get the distance to the star. All right, so let's just summarize what standard candles are. You know the true luminosity when you have a standard candle. Once you've identified it as a standard candle, you know its luminosity. You compare it to its apparent magnitude. Any luminous star that appears dim has to be far away. A dim star that appears bright must be nearby. Therefore, any star with a known luminosity is a standard candle and can be used to determine distance. All right, so the last way that we have to determine the distance of the star is through their temperature. And we already talked about how taking the temperature of a star is relatively easy because of the relationship that Annie Cannon showed us, that temperature is directly related to the light spectrum. So as long as you can see the star, you can get its spectrum, you can get its temperature. If you know one more thing, then that's a way to get the luminosity and then from there, again, go to distance. And that one thing is that if you know the stars on the main sequence, because this tight relationship on the HR diagram means once you've identified the temperature, you can place it somewhere and you know it's on the main sequence. That means its luminosity is in this range here. And you can use that as an estimate. Maybe there's a range here because it's not completely a line, but there's a small range in luminosities that it could have. And then compare it to its apparent magnitude and calculate its distance. This process, it's not really parallax, but it's called spectroscopic parallax. So spectroscopic parallax is going from the spectrum to the temperature to the luminosity, comparing to the apparent magnitude, and then calculating distance. And because it's so easy to take the temperature of a star, as long as you can see it, this gives us a way to measure the distance to stars that are really far away, even outside of our galaxy. The only catch is we have to also know that it's on the main sequence, and so that's a not so easy thing to recognize always. Stars can be challenging to locate exactly on this diagram. So in summary, we've talked about 4 different methods: the radar ranging, triangulation, Cepheid or Lyrae variables, which are types of standard candles, and then spectroscopic parallax. The key and new information here on this slide is that for radar ranging, it's just really useful in the solar system. Parallax, we can get out to the neighborhood of in our neighborhood of the galaxy, so the stars that are, within tens or hundreds of light years from us. That's possible to use parallax, stellar parallax. But once you go to the standard candles or the spectroscopic parallax, you can get out to stars that are 60 million light years away, 1.2 million light years away. So that dramatically increases how far away we can determine the distances of stars. And at the end of the semester, when we come back to studying galaxies specifically, we'll see just how important these Cepheid variables were historically to our understanding of the universe.